Okay, we're back, and we're looking at charged particles flying through magnetic fields. This is a pretty fundamental thing where, we talk about all the basics of magnetism, and in particular, we know that magnetism is created by moving charges. Now when it comes to forces, it takes fields to create forces. In particular, if you have two or more fields, in this case magnetic fields, interacting, there will be some kind of magnetic force. So on a charged particle, it could be an electron or a proton or many other types that exist out there. Fundamentally, we know we have this cross product. Okay? We saw in the lab how electron beams are deflected at right angles to the magnetic field and to the motion. So that's a cross product, QV cross B. So obviously the V part tells us that the charges have to be moving, and the reason for that is if the charges are not moving, they don't have any magnetism. Okay, so that's all fine and good, as far as like right-hand rules for positive charges, left-hand rule for negative charges. But usually we're dealing with numbers. We just want to find out how strong the force is. And so that means we have QVB times the sine of the angle between the velocity and the magnetic field. Okay, so if you have those two vectors, we can always find the magnitude of cross products for any vectors actually with the sine of the angle. Now note that the important part here physically is that your force and the motion are always perpendicular to each other. Okay, now the consequence of that is you have these particles flying around in circles. You get circular motion. And we know from mechanics that circular motion means you have an overall centripetal force. So mv squared over r is our magnetic force. Okay, now what you can get from this often, and this is what we've always used dealing with something like a mass spectrometer, is you can actually solve for the mass from this equation. Okay, so in practice, in labs all around the world, you have these mass spectrometers to identify particles or ions or different types of even molecules if they're ionized. And when you solve for mass, you'll have the charge, the magnetic field, the radius of the circle that the particle moves in, possibly the sine of some angle if it's not 90 degrees, then you define that by the speed. Okay? And we're going to show some computer simulations in a second to remind us what that looks like for a mass spectrometer. Okay, other little tidbits of this: when particles are curving and bending inside these magnetic fields, no work is being done by the magnetic field. Your particle isn't speeding up or slowing down. And again, that's because the force and velocity are perpendicular. Okay, all it does is just steer it in a different direction into that circle. The other kind of interesting thing that happens in nature, things like the northern lights or the particle detectors, like the work I used to do, is you see these things flying around in helixes, in spirals. And that'll happen because in nature, most of the time, your particles aren't going to be perfectly perpendicular to the magnetic field. It'll get some other angle. Remember though, if your particles move parallel to a magnetic field, so your angle is 0 degrees, there is no force. The sine of 0 is 0. Okay, so let's look at some pictures. Okay, here's one of the active physics simulations, and this is for a particle inside a magnetic field. It's going to start off where the particle is moving in the x direction. Okay, and let's just see what happens. Let's see how it gets bent. This is a kind of like a side view, so that the particle is going to be moving in the xy plane, and we're told the magnetic field is pointing in the z direction. Okay, straight up in this picture. On the right, this is like an overhead view. We see dots, and the magnetic field is coming up towards us as we look down on the xy plane. And right now, I'm just going to give it a little bit of x velocity. Okay. So just watching that, You can test this to see what kind of charge it is by using either the right or left-hand rule. And it turns out it's a negative charge. Okay, so keep in mind, what should happen with this if I reset it and if I change the speed. Okay, let me run this again. Get a sense of how big the circle is. Okay, so it starts at the origin, it goes up to the height of, the y-axis right there. Okay, what happens if I make it go slower? Okay, how's that going to affect the radius of the orbit? Okay, let's go ahead and run it. Notice you get a smaller circle. Okay, so the radius of your orbit is directly dependent on how fast you're going. Okay, so slow-moving particles, they get bent into kind of a tight circle, small radius, and as we increase the speed, go as fast as we can. Okay, notice you get a much bigger circle, okay, bigger orbit. Now this is, this orbit forms in the xy plane as long as your particle is moving into the field perpendicular to the field. Okay. Let me reduce that so we can see the full circle again. But this time I'm going to add some z velocity. Okay. So in other words, the particle is moving along the x-axis originally and in the z direction originally. So it's going to be kind of on an angle. Okay, so it's going to be flying into the magnetic field kind of on an angle like this. What's cool about that is part of your velocity is perpendicular. Okay, that's your x component, and that gives you circular motion. The z velocity is running parallel to the magnetic field. Okay, so there is no magnetic force on that part of the motion. So what we'd expect is the combination of those two. You should get a circle, and you should get that linear motion going up. That's where you get the spiral, the helix, the corkscrew. Call it what you want, but check it out. Okay, so notice you've got that circular motion. The bird's eye view looks the same. Okay. That's your x velocity causing that circle. But here, that circle is moving upwards because of this added z velocity. Okay, this is what tends to happen in nature. Magnetism is a three-dimensional thing, so it really helps to see it with these computer simulations. Okay, now let me go ahead and change the simulation. This is the active physics screen for electromagnetism. I was just looking at the force on a particle, and let's look at the mass spectrometer. Okay. Okay, I'm going to set this simulation up. Okay, so here's a case where an ion is going to come out here. This is our velocity selector, so we know how fast the particle is going to enter the magnetic field. The field's coming out. Okay, and we have it set for carbon. So if you have a carbon source and you ionize those atoms, and then you send them down the velocity selector, instead of getting one track, you get multiple tracks. Okay, notice how you have the two different radii here. Okay, now one of those, if you solve for it, is going to have a smaller mass than the other one. Okay, and they differ by 2 neutrons in this case. One is carbon-12, one is carbon-14. But this is what a mass spectrometer can do. Okay, remember the mathematics here. You're looking at the mass right there. Okay, so if you think about what's the relationship between mass and radius? They're both coming in at the same speed. They both have the same charge, and they're both in the same magnetic field. They enter at the same theta, okay, same angle, 90 degrees. So the bigger radius is indicative of the bigger mass. Okay, so in our picture, the blue is the bigger radius, so that would be the carbon-14, and the red would be the carbon-12. But this will happen for for all sorts of different things. Uranium, for example. Okay, U-235 versus U-238 in this case. Okay, notice a much bigger mass, so they're going to have a much bigger... This is at the same speed and the same magnetic field. We're not even going to see the thing come back. So let's make the magnetic field quite a bit stronger. Okay, it's as strong as we can make it. What should that do to your orbit? Should that make it a bigger orbit or a smaller orbit? Well, that's still kind of hard to tell. Now, let's reduce the speed. Oops. We gotta slow that thing down. Okay. Now we can see the thing bend. This happens mainly because we're talking about a much bigger mass in this case. Okay, uranium is a much heavier element than carbon was. But notice you still get the separation. It's not as dramatic, but it still does separate. Okay, so yeah, you can play these games. Here's neon, it turns out. Moving pretty slow in a very strong magnet. And look how tight that circle is. We've cut the mass down. Let's see if this makes sense. Again, the mass and the radius, okay, those are directly dependent on each other. But whereas the radius and magnetic field are actually inversely proportional to each other. You can kind of see that over here. So you can play with these simulations and get really a physical feel for what's going on. If we were to reduce the magnetic field, it's for neon again, for reducing the force on it, watch what happens. Okay, a little bit bigger radius. Okay, we can play the game. Maybe we can change the speed, increase the speed, and decrease magnetic field a little bit more. Now it comes in faster. There you start to see a separation of the two. It's a whole lot bigger radius now, because we've weakened the magnetic field and they're flying pretty fast. So again, you can get a sense of how things are proportional to each other. Key point is things move in circles, things move in spirals. You can identify isotopes and things like that. But this is all directly dependent on just the nature of magnetism. This cross product here, QB cross B. And now we can have some visuals as to what this looks like. So I hope this helps, and until next time, we will see you later.